Representing algorithms. Number 1. Understand and explain the term algorithm. So this is easy because it gives you the answer in the next column right away. An algorithm is a sequence of steps that can be followed to complete a task. This is the definition they've given you in the specification of the AQA document. That's the definition they're going to base the mark scheme on. That's the one you should learn. Make a flashcard on that. Remember that. Number 2, it says, be aware that a computer program is an implementation of an algorithm and that an algorithm is not a computer program. So these are not the exact same thing. What that means is the algorithm is a sequence of steps. A computer program often has algorithms in it. It has a lot of sequence of steps in them, but not all computer programs are really doing like a big sequence of steps to achieve something. Some of them are just maybe just outputting something to the screen, and that's not really an algorithm per se. They're slightly different things. Remember that this is your definition of an algorithm. A computer program is an implementation of an algorithm. That's the words they're using. If they use the words in the specification, that's what they're basing the exam off. That's what you should go on. A computer program is an implementation of an algorithm. An algorithm is a sequence of steps that can be followed to complete a task. Number 2, understand and explain the term decomposition. It says here, decomposition means breaking a problem down into a number of subproblems, so that each subproblem accomplishes an identifiable task, which itself might be further subdivided. Now, why have they asked us to understand decomposition right after they've understood the term algorithm? The reason is that when we want to make an algorithm for a task, we generally break it down by decomposing it into individual steps. So if you're writing the standard example, an algorithm for making a cup of tea, and your algorithm was step 1, get cup, step 2, make tea, that wouldn't be a very good algorithm to someone who didn't know how to make tea because they don't know the actual steps. So you need the right level of detail. Again, probably learn this definition that they've told you as they want it. Again, it says they can be further subdivided. So remember that you can keep decomposing a problem into its real constituent parts. So a mathematical problem, you can get that down to every single addition or subtraction or whatever. But ultimately, they're saying when you are faced with a big problem and whenever you're writing an algorithm, this is what you should do. Break it down. Break it down into small problems. That's what you should always do, because then a big problem becomes lots of small problems, and small problems are easy. Number 3, understand and explain the term abstraction. These 3 terms obviously are words that they want you to know, probably because they're going to give them to you as a 1-mark question of define this. So abstraction, again, they give us the definition in the specification. Don't look it up on Merriam-Webster or an Oxford English Dictionary. Use the definition they have given you in their own specification. Abstraction is the process of removing unnecessary detail from a problem. That's the definition you want to use. What does abstraction mean? Well, typically it means we're breaking down. What does abstraction mean? Typically it means that we are removing the unnecessary detail that isn't useful to us when we look at a problem. So a good example that people tend to use is a London tube map. The real tube map is really crazy, and the trains crisscross over each other 100 times and go all the way around weird routes to get to the stations. And that's very useful to you if you are designing a tube network. But if you just want to get from A to B on the tube, you don't need to know that, and you'd much prefer this conventional tube map where they've neatened that out and pretended that all the lines are perfectly straight and look lovely. And what they've done there is abstraction. They've removed unnecessary information from the problem. They've removed information from this complicated map so it looks simpler and it's easier for us to understand. Remember that abstraction is kind of specific to who is using it. So as I said, a London Tube engineer doesn't want to use a normal tube map because that's not enough information for him or her. Abstraction is getting rid of the information that's not useful to you. I guess if you use the making tea example again, if I was writing an algorithm for making tea, I just need to tell you, pour water into a cup, that's fine. But if you were a chemist, you might want to have a detailed explanation of what chemical reactions are going on and quite how the tea is diffusing and separating. That's unnecessary information to somebody who's just making a cup of tea, and so by abstraction, we remove that unnecessary information. Use a systematic approach to problem solving and algorithm creation, representing those algorithms using pseudocode, program code, and flowcharts. This is the slightly more complicated bit, and we'll go through some examples in the next video about quite how all these things work. But it gives you an exact definition. the specification, download it, it's gold dust, it tells you everything. It says any exam question where students are given pseudocode will use the AQA standard version. And there's another document here which tells you exactly how their pseudocode works, that they want you to use this, and that's how conditionals should look. And obviously you don't understand any of this yet because you're just starting out, but it tells you exactly how the thing should look. Use that. It also says exam questions will indicate the form of response expected. For example, it will give you an algorithm as a flowchart and ask you to write some pseudocode for it, or it might give you some Python code or some C# code and asks you to write a flowchart for that code. And we'll do some of this. This is a bit more of a skill, so we'll do some of this in the next video. Explain simple algorithms in terms of their inputs, processing, and outputs. So it says students must be able to identify where inputs, processing, and outputs are taking place in an algorithm. This essentially just means understand the algorithm you're looking at, and the way you're going to do that is just by practicing lots. You practice looking at lots of algorithms, converting them from one to the other, and we'll make loads of videos on that. You can do loads of practice, get used to algorithms. When you're programming, you get loads of practice in algorithms because that's what you'll be working with predominantly. So this should be pretty easy to do. In terms of the definitions of these words, an input is anything that the user is inputting into the system. So for example, typing something onto the keyboard. An output is anything the system is processing back to the user. So maybe it's writing something on a screen, and the processing is in the middle. It's what the program does with the inputs to turn the outputs. So this could be as simple as when you click the print button on your computer, you're inputting a mouse click, and your computer is outputting a document to the printer, and in the middle it's processing how it's going to print that. Or it could be something more complicated, like in a video game. If you move your mouse to the right in a first-person shooter, that mouse movement is the input. The computer will process that, see how far you've moved, what direction, and how it should change the screen. And the output is the way that it changes the graphical frames on your screen so that your character moves in that game. As I say, input, user to system, output, system back to user, processing, anything the computer's doing in between. Finally, define the purpose of simple algorithms. So students should be able to use trace tables, more on those later, and visual inspection to determine how simple algorithms work and what their purpose is. So again, you're going to be seeing examples of algorithms, and they're going to tell you, they're going to ask you, what does this algorithm do? Or they're going to ask you to trace through and see what would happen if you ran this algorithm with a equals 3 and b equals 4. And for more of how this and these things work, see you next time.